Hello, everyone. Welcome to pre-lecture 7. This is going to be our pre-lecture for before class on Tuesday. All of this material will be on quiz number 4. And so just a reminder to be studying for quiz number 3, which will take place in class on Tuesday, but this material will be for quiz number 4. All right, and so with this lecture, we're starting chapter 12, which is kinetics. And so the field of kinetics in chemistry refers largely to how fast a reaction will proceed. And so if we are talking about kinetics, generally the question we are asking is how fast? Obviously, this can be important to understand how quickly something will be consumed or formed. It can also tell us about a reaction mechanism, which is something we'll talk about next week, as well as the different steps within each chemical reaction. Okay. This is generally described in terms of rate laws, and so we'll define what that is in this video and then expand upon it during this week. Okay. Right, so the rate of a reaction can be generally defined as the change in the amount of a reactant or a product per unit of time. And so all of this is, we're measuring something, a change, and dividing it by a time, right? So say we have this example here. This is the decomposition of hydrogen peroxide, where we have H2O2 turning into 2 waters and 1 oxygen. And so if we wanted to express the rate of that reaction, our rate expression would be that the rate of our reaction, decomposition of hydrogen peroxide, is equal to the negative change of the concentration of reactant, because we are losing reactant, so that's what makes it negative, over some amount of time interval. Okay, so that could be per second, per minute, per hour, largely depends on how fast your reaction is going. Okay. And if we wanted to write that in more specific mathematical terms, we would express it as the rate of H2O2 decomposition is negative, basically time 2 data point minus time 1 data point, and then time 2 minus time 1. And so we can, of course, abbreviate those using delta, which uppercase delta here, this triangle, is a symbol for change. So the change in our concentration of H2O2 over the change in time. And so if we were to do this, this is an example from our book. So if we find the change in H2O2, we can take a data point every 6 hours and then determine the rate of decomposition by just, again, dividing one by the other. Okay. And so you might notice, if you pay close attention to these numbers, that our rate of decomposition actually gets slower over time. This is fairly common. We'll talk about maybe why that is and different ways we can express rate, right? There are different ways we can express rate. So for example, we could say the average rate if we averaged all of our rates that we have here. We could also use the instantaneous rate. So maybe we only want to report the rate for our first data point here. We could report that as the instantaneous rate. And we could also determine the initial rate, which is, the initial rate is our first data point. The instantaneous rate would be the rate at any one of these single data points. Sorry for that confusion. Okay. And so if we express this graphically, it would look something like this, where our very first data point would be our initial rate, where again, we have some amount of change in our chemical over some amount of change in time. And we could get a slope for that line and report it essentially, right? If we get an instantaneous rate, it would be any point along there. And then if we were to average those, we could get an averaged rate, of course. Right, and so if we think about a stoichiometry of our reaction, that will also affect how our rates are calculated. And so if we have coefficients shown by lowercase a and lowercase b here, we take 1 over the coefficient and multiply it by the change in that concentration of the chemical, in this case A, over our change in time. And again, anytime we have reactants, we're going to put a negative sign in front. Anytime we have products, we're going to be forming those. And so we're going to have a positive rate of formation for the products. Okay. So here's a chemical reaction where we have 2 NH3 producing N2 and 3 H2. And this is a chemical reaction. So if you want to pause the video, you can think about how this rate of reaction would be expressed based on what we just talked about. And if you want to pause it, you can, but I'm going to go on. So our rate would be equal to -1/2 change in our concentration of NH3 over our change in time, which would also be equal to the change in N2 over the change in time, which would also be equal to 1/3 of the change in H2 over time. Okay, so that's how we would apply our stoichiometric coefficients to determining our rates of reaction. And so again, if we put this on a graph, this is the same reaction where NH3 is our reactant. It is going down in concentration, and we have an instantaneous rate there. That would be at the same point, we would have basically 3 times the rate of formation of H2. And so in order to get those rates equal, we would take 1/3 of that. That's where that 1/3 comes in. And then for N2, that would be, I believe the coefficient was just 1 in front of N2. And so that's why it is our flattest slope, okay? Right, that's the introduction to kinetics. We'll of course do some problems in class, talk about different ways to measure rates. I hope you have a good day. Let me know if you have any questions. Otherwise, see you in class on Tuesday for quiz 3 and lecture 7.